Hey guys, it's Logan again. Welcome back to another video. This is the first video of a small series where I'm going to show you guys how to create a randomized level generator once again, but this time it's going to be kind of algorithm based. Well, it was algorithm based before. We're going to be using a breadth first search algorithm to ensure that a maze has connections all the way through. And what do I mean by that? And I will show you in this small example what we'll be creating. So first off, it asks me how many obstacles do I want to place in my room or try to place in my room. I'm going to say 150 for now. That's my default. And I hit OK. And you can see it randomly places obstacles. Now this doesn't look impressive. You're probably thinking, oh, I could do that pretty easily. But if I put in maybe 400 obstacles, so I just hit space, you can see that it's something more generated, that I have more randomness to, right? And I think I actually just realized something that I don't like that I wanted to see in the code, but I'll do that afterwards. But as you can see, we have connections all the way through. There's not a single point on this open space that isn't accessible. You can use this algorithm, and you could even create random maps like this. I'm going to be showing you how to implement the A* pathfinding for enemies, and you could have enemies randomly spawn in here and kind of chase the player around, and he's kind of shooting at them, you know. I'm going to show you how to implement the cover system that's in one of my other videos that will allow enemies to actually run away and hide from the player, along with the A* pathfinding. Another thing you could do with this is have it warp you to the other side if there's a spot open, and there's all kinds of stuff you could do. And this isn't just limited to creating a map like this. You're going to learn once again how to use a breadth first search algorithm, which if you're ever going to take computer science, you're going to have to learn that and the depth first search. We're going to go over a couple data structures like the stack data structure, the queue data structure. We're going to be creating our own types of structures for coordinates, and I'll show you how to do that. We're going to be using two-dimensional arrays, one-dimensional arrays, stacks, queues, lists, you name it. I'm going to show you how to do all of that. So the first thing I'm going to talk about in this video is the different data structures and kind of what we'll be using. So I'll kind of show you a little bit of this code first. So this entire thing is made out of an initialize room code and a map is accessible script, which is our depth first search algorithm, which is a graph traversal that we'll be learning about. Okay, so this is our depth first search algorithm. And basically it's using the queue data structure. We're not ready to talk about it quite yet, but we'll get there. And this is kind of our initialization. So we're going to create a coordinate structure that we're going to be able to add a coordinate. You see here we have add coordinate. We can add an XY coordinate to our coordinate data structure, and we don't ever have to really interface with the actual array that we're using after we create our structure. So we have our structure over here, and we just use add coordinate, get coordinate. We can get a X or Y coordinate from a specific position. You can see I want to get the X coordinate, so I'm putting X here, I'm putting Y here because I want to get the Y coordinate at that same position. We once again get coordinate, and I have some other stuff like get coordinate list size and shuffle coordinate list that we use right here. So the shuffle coordinate list is another small algorithm we'll be going over, and it basically is a way to shuffle a two-dimensional array around, or really shuffle a list around, but we're using a two-dimensional array in this case. So the first thing I want to talk about before we get into all this is the different data structures. So there's two that are similar data structures, but they're completely different at the same time. We have a stack and a queue, and if you already know about a stack and a queue, you probably don't need to go over this again, but a stack is a Philo data structure, first in, last out. So what does that mean? Well, if I grab my rectangle, yes, commit tool changes. If I grab my rectangle and I insert a couple elements into our list. So for stack, you use ds list push, I believe, or ds stack push. And the reason it's called push is because it's pushing the value that we want to enter, the data, onto the bottom of the list or the top of the list. So our first data gets put in, and then we go to maybe a second data, and it gets pushed. You see it's on top, and then we maybe go to do push again and push a third item, and then we push a fourth item on top of that. So these could all be numbers like 0, 1, 2, 3, but I'm just using colors to represent that. So now when we want to access things inside of this stack, we can't get something off the bottom. That doesn't work with the stack structure. We can't get something here. We can't get something here. We can only retrieve the first item from the top. So what we use is ds stack pop. So it'll actually pop the top off. So let's say I do, oops, give me my, okay, I accidentally did this, but it's neat. It's going to work. So it popped that top element off and then saved it. We could save that top element to like a variable. So we could say, hey, I want to get the top color. So I say color equals ds stack pop. And it pops that and returns that color. And then I do pop again. It gives me the green. I do pop once more. It gives me the gray. I do pop once more and it gives me the orange. Now I have nothing left in my stack. Okay, so how does that differ from the queue? Well, let's say we did the same thing with the queue, but instead you don't use push, you use in queue, which is that's the same thing as push kind of, but you use the keyword in queue. So you use ds queue in queue, and it puts an object here, and then we put the object here, the next element, and then we put the next element here, and then the next element here, just like we did on the stack with the in queue. The difference is now we're going to be grabbing this piece first. So I have no way of doing this. So we're going to be grabbing the first one that we put in first, given FIFO, which is first in, first out. So the first one we put into our structure, the first one that comes out when we call DQ. So then we DQ again and it comes out. Then we DQ again and it comes out. And then we DQ again and it comes out. So as you see, in this structure, our yellow was the first or the last one to be returned, whereas in this structure, the yellow was the first one to be returned. So you see they're similar, but they're opposite at the same time. Now, what different ways do we use these two? Or why would we use these two? Well, a stack is really good for backtracking. Let me give you an example. So I'm going to use a color, let's say yellow, to represent our checked spaces, or let's say we're adding to our stack. So imagine I'm adding spaces to our stack in this maze. I'm trying to find a way to, like this point here, okay? But we're starting at this point, okay? So this point gets added, this coordinate would get added into our stack, and then we keep adding into our stack as we're randomly kind of moving about our grid, right? So we keep moving and we keep choosing a direction to move and adding all of these to our stack. Remember, all these yellows are now in our stack. And we get to this point and then we try to move a new direction, but there's no more directions to move, right? We're kind of out of options. So we can actually use a stack to backtrack to a point to maybe where we did have other options. So maybe what we do is we pop from our stack. So we pop this element from our stack and then we retrieve the next element. And now this element, we could say, well, let's choose a new direction, okay? And we'd have to store this in like a list of checked spaces to make sure this doesn't get picked over and over, right? But if, let's say we mark this one as white now, okay? So this one's now marked as checked, okay? Or solid, don't go here, basically. And then, oh shoot, this is gonna be kind of odd, but let me go back to black. Sorry about this. Go back to black. Okay, so we popped that from our stack, and now we're at this position. We're saying, hey, check for new positions. Well, I'm not finding anything. So it'll once again pop, hey, we're at this coordinate, check for new positions. Well, it's not finding anything. We've checked all these. So it pops once more, says, hey, check for a new position. Well, we can now. It finds down here, and then it starts moving once more. Okay? And let's say it gets to here. Okay? It for some reason went up. Well, let's check for, let's pop from our stack once more and check for a new position. Well, we have somewhere else we can go. We can go right here. So then we search and search, and it finds our point. You can see how we used a stack to kind of backtrack where we were at in our maze. So you could actually write an algorithm for this just using a stack, and it would be pretty simple. So I'm going to backtrack all this stuff. And you can see this is kind of basically, actually, this is a good example. When you're in a paint program, it's adding your actions to a stack, okay? And when you hit Control Z, it's actually popping those actions from the stack. So it's backtracking. So that's a kind of an example that you can use a stack for, is backtracking. So anytime you might need to backtrack steps, you can add things and use the stack data structure. Okay, so what makes the queue a bit different? Well, why would we use a queue? Well, we can use a queue to expand and check every space. You could see a stack would take a really long time, and then by the time it got back here, we might not be able to see all the spaces. We'd have to go this way. A stack kind of goes as deep as it can go first, and then it goes kind of back. So it would always go as deep as it can go until it can't go anymore, and then it will backtrack and go as deep as it can go until it can't go anymore once again, okay? A queue, on the other hand, will go as broad as it can go. It's kind of like a fill. So, for example, it would look more like something like this, and it would go kind of in broad strokes instead of going deep and then backtracking. And I'll show you how this works. So, this is going to be a bit more complicated, but bear with me. Well, it's not really more complicated. It's more complicated to visualize. So, let's say we start here. This is our first queue. And I'm actually going to, okay. All right, so let's start with yellow, okay? And I'm gonna have kind of a smaller version now of this. Okay, so we have our yellow, and our yellow gets added. I actually wanna do this. So our yellow gets added to our queue, right? And then let's say we want to, for our example, we're going to be adding all the neighboring spaces to our queue. So we add a red to our queue. And then, how do I get to my fill rect? Shift R, okay. So we add our red to our queue. And then let's add a blue to our queue, because we're adding our neighboring spaces. Shift R. And now blue is added to our queue. Now we want to add maybe pink. And pink is now added to our queue. So we've added all of our neighboring spaces to our original queue. And we actually, before we did all this, we actually popped this out. We retrieved that coordinate, which was right here. So this got popped out of our queue. And then using that coordinate, we checked all of the neighboring spaces and added those into our queue, okay? Okay, so what happens now? Well, we repeat the process until our queue is empty, okay? So we actually, we don't pop, we dequeue our next item, which remember is going to grab it from the bottom, which is going to be our red. So I'm going to kind of fill in our yellow. Our yellow is checked now. I'm going to use white to fill it in. Our yellow's checked, so it's gone. We already checked that spot. Actually, let's use a gray for the checked values, like a light gray. Okay. So our light gray is checked values. Okay, so now we pulled our red off. That's where we're checking, and we're adding the neighbors of the red now. So I'm going to go back to using yellow because we have that color available once more. So yellow gets added. Shift R. Yellow gets added, and now we want to add its other neighbors. Remember, gray's already checked. We're not re-adding that. We're keeping track in a list of everything we've already checked. I'm not showing you that portion yet. I'm trying to keep it simple. So we add the next neighbor to our red, and it gets added to our queue. Remember, it's added to the top, but we're grabbing our values from the first one added. Remember, the oldest one in our queue now is blue. So I need to add this one to our queue. Oh, come on. So now our peach is added to our queue, and we've now added all the available neighbors. Remember this, we would check this neighbor, but we'd say, oh, there's an obstacle there. We're not adding it to our queue. So our orange gets checked. Well, now where do we go? We go to our blue. So, oh, come on. So we dequeue our blue. We dequeue our blue, and it gets put as the checked. Didn't we check? We checked red too. Now our red's checked as well. So we dequeue our blue, which was here, and we add its neighbors to our queue. Okay? And, well, what neighbor is going to be added? Well, this one's going to be added. We're going to use red again. And it's added once more to our queue. All right. So we've added all the neighbors of that blue. Now we grab pink, our oldest value in the queue. Okay? So we dequeue the pink. So we need to color it that color. And then we dequeue it. Oh, come on. This is really hard to keep track of all these colors, guys. All right, so we dequeued the pink, and that was this position that we're checking right now. And we're adding its neighbors. We don't add this one. We don't add this one. We don't add this one because we've already have this in our queue. Instead, we add the bottom one, and we can just use a purplish color. And once more, that gets added to our queue. And you can see this process repeats over and over. And you can see we're slowly filling out. It's like a fill. Like if you were to use this fill, it could be using a similar algorithm. It's slowly filling outwards, okay? Until eventually it's going to have every space checked. And once that happens, there's going to be nothing left in the queue. And that's when we exit out of our loop that we're going to be using. We're going to be using a while loop. So you see how this kind of expands. And I'll kind of go backwards now using Control Z, and you'll kind of see how it all shrinks back together. And again, this would have repeated until everything is full, okay? And everything's kind of shrinking back together. All right, that's it. We're just going to add each space, and using the queue function, it's going to go back to the oldest. So it's slowly going to fill out until probably these are going to be the last edges ever added to the queue, are going to be the furthest away, okay? Your furthest edges from your space are going to be added. So this is good for searching, how we're going to be searching, and we want to check to make sure all the spaces are connectable, and I'll show you how that's going to work. But the big thing is knowing how the queue function works and kind of what it can be used for. Well, it can be used for these broad strokes, okay? So to make sure that we're going out in a loop, while stack can be used to check kind of deepness, how deep something is, or use it for backtracking. And these are used for, once again, graph traversals. And I could show you graph examples, but I might link a couple videos below if you want to see what I mean by used for a graph. But in our case, this is a type of graph because we have connected edges to the spot we're checking. So this would be like an edge, and these would be two vertices. And then this would be two vertices between linking these two, and these would be two vertices. And again, these would be edges, an edge, and these would be other nodes, okay? So this is a type of graph, so you could think of it like that. So again, we're using breadth first search, which is what I just showed you, instead of the other one was actually depth first search. If we wrote the algorithm using the stack, it would be a depth first search. It goes deep and then it kind of searches from there. Okay, so I think I've kind of demonstrated enough for you to kind of see how queues and stacks are useful for these kind of search methods. So if you enjoyed the video, please like and subscribe. And in the next video, we're going to be going over creating our actual coordinate structure that we'll be using. That's going to make this a lot easier for us. So again, like and subscribe if you enjoyed the video or you learned anything, and I will see you next time.